Sup Sigma fam, it's your boy Chris. Welcome to our first episode, our maiden voyage, our opening chapter, if you will, for our first 5 in 20 segment. So if you're not familiar with the idea of what this 5 in 20 segment is all about, pretty much I'll be targeting certain concepts in prelim and HSC physics. These are concepts which I generally think that students kind of struggle with and need a bit more exposure to in terms of solving problems. So as you've probably found out by now, Module 1 and Module 2 in Year 11 are really heavily focused on problem solving, as is Module 5 and the first half or so of Module 6 in Year 12. So it's pretty important for us to get on top of our problem solving techniques to make sure that we can basically just, pwn any question which they bring forth to us. Okay, so there's already a whole range of great resources out there available for you guys in terms of actually going through the theory and the content side of things when it comes to HSC and prelim physics. But yeah, there's just not that much on actually problem solving. So seeing as it is such a major part of HSC and prelim physics, thought to kind of do this little thing for you guys, especially for my future Sigma fam who unfortunately were unable to join us in the prelim physics course because there's just too many students and I had to put you 60 or so students on my waiting list. So kind of, hashtag sad face about that, but I'm super pumped to hopefully, work with you guys throughout your year 12 studies and help you pwn all the HSC physics stuff. So basically really happy that you've joined and really happy that you're joining me for this first kind of go at our 5 in 20. If you want to go through it with me, best thing for you to do is to look at the description. There'll be a little link for you to follow which will enable you to access the worksheet. So download the worksheet, print it off, and either have a go at it before I go through the questions, or if you want to go through it with me, by all means just wait for me to go through it with you. Without any further ado, let's sum up those SUVATs. Broski McBrosefsons. So we've got a stationary car speeding up to 15 meters per second in 3 seconds. Find the magnitude of the car's acceleration. First thing that we need to see is, well, what do we actually have from the question itself? So we've got that the car is initially stationary. So that's telling us that our initial speed is 0 or initial velocity is 0. So therefore our value of u is 0. Speed's up to 15 meters per second. So v is 15 meters per second. In a t of 3 seconds, find a. Okay, so we just go through our SUVAT, which one's the more logical one to use for this scenario. You want to find A, given that you have V, U, and T. It's nothing more than just the acceleration equation. Okay, so A is equal to V minus U over T, and then pretty much we just plug in the numbers. Okay, so there's nothing exciting to this question. Our final speed is 15. Our initial speed is 0. Our time taken for that change to occur is 3 seconds. So therefore our acceleration is just 5 ms to the minus 2. Now notice in this question, you're not given any direction of the velocity vectors or anything like that. So if you want to be kind of like Uberleap band 6-ish kind of thing, best thing for you to say here is that the acceleration is 5 ms to the minus 2 in the direction of the final velocity of the car. All right, so on to question 2. So question 2, you notice it's a bit of a longer question, but you also notice that we're given some directions. We're given the direction of the initial velocity vector, and we're also given the direction of the acceleration, and they're in fact the exact opposite direction. Okay, so our initial velocity is towards the north, our acceleration is towards the south. So with vectors, if you have two opposite directions in terms of our vectors, we just basically say one's positive and one's negative. It is kind of arbitrary which one you define as positive and negative, but I always try and get my students into good habits, and that is pretty much by convention we say that north is positive and south is negative. Okay, we just kind of keep that going throughout all of our studies so that we just don't get confused, when it comes to some sort of out-of-the-box question. All right, so I would say here that the 8 meters per second north is going to be positive 8. It's my initial velocity, so therefore u is positive 8. The acceleration is 3 ms to the minus 2 south, so therefore my acceleration is going to be negative 3. Time given 5 seconds, so find the final speed of the car. So again, with the SUVAT, it's really awesome if you can kind of think about the question in terms of the different variables. So not what's the final speed of the car, think about it in terms of a SUVAT. So it's saying find V. V is the final speed of the car, or magnitude of V is the final speed of the car. Find the magnitude of V given, what do you know? You know that U is positive 8, you know that a is -3, and you know that t is 5. So find v given u is +8, a is -3, and t is 5. Okay, and once you do them kind of like that, then you just look at which equation you need to use. Well, here I need to find v, so v needs to be my subject, and on the other side of the equation, it's got to be the stuff that I know. I know u, a, and t. Awesome. There's v is u plus at. And legit, you plug in some numbers. U is +8. Again, our a is -3, and our t is 5. Okay, so when you sum all that up, we get v is -7, but the question doesn't ask for velocity. Okay, the question asks for speed, which is just the magnitude of our velocity vector. Okay, so magnitude of our velocity vector is therefore going to be 7 meters per second. Sick, easy. Part B, the time taken for the car to become stationary. Again, think about it in terms of a SUVAT equation, okay, in terms of the variables. The time taken for it to become stationary. So what is the value of t when v is 0? Okay, given u is +8 and a is -3. So it's actually the same equation. It's the acceleration equation, except you're solving for t. Okay, we're solving here for what is the value of t when it's stationary. That is that v is going to be equal to 0. Our final speed is going to be equal to 0. Our initial speed's given in the question, +8, and our acceleration in the question is -3. Okay, so it becomes 0 minus +8 divided by -3, and that gives us 2.7 seconds, again, or thereabouts. Okay, so 2.7 seconds is the time taken for the car to become stationary. The total distance covered during the 5-second interval. Now, this is actually a bit trickier than it seems, because it says distance. Now, distance, like because the car turns around, it starts to travel in the opposite direction. Now, with distance, we still care about both of the legs of the journey. Okay, so what I mean is, if it takes 20 meters for it to turn around, and then when it turns around, it travels another 15 meters, then the total distance traveled is the sum. It's the sum of those two legs. It's 20 plus 15. If I wanted the displacement, awesome, I can just do it all at once. But with distance, we need to consider each individual leg and then sum the distances for each individual leg. Okay, so our first thing, we figured out the time that it takes for it to turn around, but I know it's a bit easier for us to use this v-squared equation, because with the v-squared equation, it's always the same. The conditions are always the same, and that is it turns around when v is equal to 0. Okay, so here we've got our v squared is u squared plus 2as. I want to solve for my distance covered in this first leg, so I want to solve for my value of s, given that v squared is going to be equal to 0. So therefore, my first leg is just going to be -u squared over 2a, okay, which is going to be -8 squared divided by twice of my acceleration of -3, which gives me a displacement for that first leg, 10.67 meters. Okay, so 10.67 meters is the displacement or the distance covered in the first leg. And then looking at the second leg, much the same thing, okay, except here I'm starting with a speed of 0, okay, and then I'm finishing up with a speed of 7. Okay, remember we've solved in part A that the final speed is 7 meters per second. So therefore it's going to be not -u squared on 2a, but rather v squared on 2a. Okay, given that my u is initially 0. U is initially 0. That doesn't make sense because u is initial. Okay, anyway, so u is 0. So -7 squared divided by twice my acceleration gives us 8.16 meters. So the total distance traveled is actually the sum of those two numbers, whereas the displacement would actually be the difference. Okay, so which we'll find out here. Okay, so when we do our ut plus half at squared, so we could do, this whole version here, given initial speed is our 8 from the question, and the time is 5, our acceleration is -3, so we've got minus a half over here, so -3 on 2. We end up with 2.5 meters north. Or we could have just done, well, it goes 10.67 meters north in the first part of the journey, 8.16 meters south in the second part of the journey. What's the difference? That's going to be the overall displacement, and that indeed is 2.5 meters. All right, cool. That was a bit of a harder question, a bit of a longer question. Now on to question 3. Question 3, champions. A car is initially moving with a velocity of 14 meters per second west, undergoes constant acceleration for 7 seconds to reach a final speed of 35 meters per second east. So again, two different directions, opposite directions. Generally, if you think about north, east, southwest, we say that north and east are positive, south and west are negative. And again, I'll keep going with that. So this 14 meters per second west, the initial speed is going to be negative for me, and the final speed of 35 east is going to be positive. Okay, so north and east positive, south and west negative. Find the acceleration of the car. So what do we have? We've got the two speeds. We've got the initial and the final velocity. we have the time taken to move between those two different velocities. So therefore, we should be able to figure out our acceleration just by using our regular acceleration equation. So v minus u over t, making sure we get the signs correct. Again, my final speed or final velocity is 35 east, so positive 35. My initial is 14 west, therefore negative 14. So it's 35 minus negative 14 divided by 7, which gives me a nice number, 7 ms to the minus 2. It's a positive number, which is telling me that the acceleration is towards the east. Okay, so as with all vectors, make sure you have, magnitude, you have units, and then you have direction, okay, in order to give you your best chance of getting full marks. Okay, being a teacher, I know sometimes we mark things, specific little things, which you probably can't usually guess what we're marking. But I mean, if you show all working, you have, correct number of sig figs in your question, you have the right magnitude, right units, and you have the correct direction, then, odds are more than likely you're going to be getting full marks. Velocity of the car after 4.5 seconds. So again, consider what you have. You've got V, you've got velocity of the car after you don't have V, you have U, you have the acceleration, which you just figured out from part A, and now you have T. So it's the same equation again. Okay, it's just that we're going to rearrange and make V the subject. That's the thing that we need to solve for. Okay, so our U once again is going to be negative 14. Now our acceleration is going to be positive 7. Okay, 7 east. East is positive. And it does that acceleration for 4.5 seconds. So therefore our final velocity is positive 17.5, which means 17.5 meters per second towards the east. All right, part C. The time taken for the car to have a displacement of 10 meters to the west. I mean, there's a couple of different ways that you can do this question. One of the ways involves the use of quadratic formula, which again, in my experience, if students are going to stuff up a SUVAT equation, it's when they try and use a quadratic formula. If you're full pro with a quadratic formula, by all means do it, and you can do it pretty quickly. But I want to show you a different way of doing it just to eliminate the need for the SUVAT. Okay, so the time taken for the car to have a displacement of 10 meters towards the west, the first thing that we can solve for is what is going to be the final speed. Okay, so we use our v squared equation to find what's the final velocity for our car when it's got a displacement of negative 10. Okay, it's got a displacement of 10 meters to the west. And this gives us two solutions. Okay, so we get v squared is 56, therefore v is plus or minus about 7.5. Okay, so v is plus minus 7.5 meters per second. We can then use that value of v in the acceleration equation to solve for our different values of time. Okay, so we can say the first time that it's going to happen is v minus u over a. We get minus 7 minus 14 over 7. So therefore, our first time is going to be around about 1 second. Our second time that it happens is going to be when it's moving back towards the east, so that its velocity is plus 7 instead of negative 7. Okay, and therefore we end up with a time of around about 3.1 seconds. All right, so yeah, around about 1 second and 3.1 seconds would also be the two solutions that you get if you use the ut plus a half at squared equation. But yeah, totally up to you. If you're pro with the quadratic equation stuff, by all means do that. And I do want to preface this. I don't know preface because preface means before, but whatever the one after is. I had a student who's state rank 4 unit maths who stuffed up quadratic equations. So just be careful. You want to minimize the chance that you have those brain farts in your exams. Okay, and quadratic formula, trust me, all the teachers know, quadratic formula in physics is something that students tend to have the brain farts on, for whatever reason it is. State ranking 4U maths kids, does conics in his head, can't do quadratic equation. GG. All right, so part D. So we have there the time taken for the car to travel a total distance of 40 meters. I just remembered conics is not in your new syllabus. You lucky things, you parametrics I suck at. Okay, so the time taken for the car to travel a distance of 40 meters. So again, this is the tricky question because it's not displacement, it is distance. So distance, you need to take into account both the legs. The ones going away from your current position, the ones coming back towards you, need to sum them. Okay, so first thing that we need to figure out is how far has it gone when it turns around? Okay, so what is the value of displacement when our v is equal to 0? This is telling me how far it's moved away from our initial position. Okay, so u squared plus 2as, I can then solve for my first value of displacement, minus 14 squared over 14. Geez, I wonder what that is. I bet you my 4 unit math kid wouldn't be able to do this. So we get 14 meters. Okay, so 14 meters is the distance that it travels before it turns around. Okay, and just to kind of figure out, like you can then use the ut plus half at squared equation to solve for time. I mean, and you see that it's 2 seconds. Alternatively, you could just use, t is v minus u over a. Okay, and it comes out as being 14 over 7, again, which gives you 2 seconds. Okay, so 2 seconds for the first leg. And then we need to find out, well, it's gone 14 of the 40 meters. How many meters is remaining? Channel my inner 4-unit student again. 40 minus 14 gives 26. So the second leg of the journey, when it's kind of heading back towards its starting position and then moving past it, it's got to travel 26 meters. So we can then use our ut plus half at squared equation again, use a value of s as 26. So the second part of the journey, it moves 26 meters. It's turning around, so its initial speed is 0. So therefore, it's just s is basically half at squared. Okay, a is 7, as we figured out in part A. We can then solve for t, the time taken for it to go 26 meters, and it's 2.7 seconds. So it takes 2 seconds to turn around, and then another 2.7 seconds to go the further 26 meters. We sum those two times, we get 4.7 meters for it to travel in total those 40 meters. All right, question 3 is done as dinner. Let's go into question 4. Question 4, homies. Car is initially traveling at 5 meters per second north. It then accelerates 2 ms to the minus 2 north for 7 seconds. Finally, it undergoes constant acceleration to come to a rest after another 5 seconds. Find a couple of things. The acceleration of the car in the final 5 seconds. So firstly, we need to figure out what is the final speed of the car after the first section. So it starts at 5 meters per second north, accelerates then at 2 for another 7 seconds. What is the final speed? It's going to be 5 plus 2 times 7. Okay, and that's going to give us a final speed of 19 meters per second, this being towards the north. How that's going to help us is then we then know like the initial speed when it starts to negatively accelerate. I hate saying decelerate, so let's never, ever, ever say decelerate. So the negative acceleration begins when it's going 19 meters per second. And think about it in terms of a SUVAT. Find the value of A. If our U is 19, our V is 0 because it becomes stationary, and our T is 5. So it's just our acceleration equation again. So it's 0 minus 19 over 5, which gives us negative 3.8, which means 3.8 ms to the minus 2 to the south. Okay, remember, north is positive, south is negative. The total distance covered by the car. So again, if we've done this a couple of times now, it's the tricky type of question where you need to consider each leg of its journey. Okay, so the leg, before it turns around, and then the leg after it turns around. You never know, sometimes it might turn around again. Okay, so each of those, we need to sum those legs to find total distance. Okay, so firstly, let's find the displacement over the first 7 seconds. Okay, so we have ut plus a half at squared. We know the acceleration, we know the initial speed, we know the time over which this occurs. So therefore, we can find what our displacement is. Okay, so we've got 84 meters for the first leg. You could use the v squared is u squared plus 2as for that to find out our value of s as well. So we've got 84 meters for the first leg. And then we have the second leg. So the second leg is when it's going 19 meters per second, but it comes to a stop. Okay, so we know that that takes 5 seconds. And so we use ut plus half at squared again. We can then find what the displacement is for the second part. Okay, so our initial speed is 19. Our acceleration is negative 3.8. So it's 19 times 5 plus negative 3.8 over 2 times 5 squared. And that gives us the displacement for the second part of the journey of about 47.5 meters. All right, so sum up the two, the displacements during the two parts of the leg, the two different legs. That is going to be our total distance covered. Okay, so therefore we end up with our total distance covered of 131.5 meters. Oh man, going to be cutting it tight for these 20-minute video. On to our last question, question 5. What a question to finish up on, boys and girls. Question 5, car travels at 30 meters per second past a stationary police car. After the car passes, the police car then immediately begins pursuing the car and accelerates at 4 ms to the minus 2 until it reaches a constant speed of 40 meters per second. Okay, that's a little bit tricky because it's not the regular type of question where the police car just accelerates until it catches up. Here it's accelerating to a certain point and then it's going a constant speed thereafter. How much time has elapsed when the police car catches up to the speeding car? So we need to come up with expressions for displacement for both the car, the naughty boy car, and also the police car. Okay, so our displacement for the regular car is 30 meters per second. It doesn't accelerate or anything like that. So we just look at distance is speed times time. Okay, so our 30 meters per second for a certain time interval t1. You notice the police car has two different types of motion. It's got its initial motion where it's accelerating, and then it's got a state of uniform motion after that, okay, uniform velocity. If it's accelerating at 4 ms to the minus 2, how long will it take to reach 40 meters per second? It's just going to be 10 seconds. Okay, change in velocity, so 40 minus 0 divided by 4, which is our acceleration, is going to give us a time of 10. So the first part of its motion is ut plus half at squared, but u is equal to 0, so it's just half at squared. Okay, so our displacement, or our distance covered for the police car, first part of its motion, half at squared, where a is 4, and the time that it's accelerating for is just 10 seconds. So it's a half times 4 times 10 squared. And then we have the uniform motion part of its journey, and that is going to be expressed as uniform velocity. So this is going to be speed times time again. The uniform speed of 40 multiplied by the time. But what is the value of time? We have that the car goes for a time of t1. The police car then accelerates for 10. So the remaining time between t1 and 10 is t1 minus 10. Okay, so that's the time for which the police car moves at a constant speed. So we've got the displacement of the police car is half at squared, so half times 4 times 10 squared. That's the displacement for the accelerating portion. And then 40 outside of t1 minus 10, which is the displacement or the distance covered for the constant velocity portion. All right, so we then have to say that they're both equal to each other. That's the definition of part A. How much time has elapsed when it catches up? The displacements are equal. So we end up with 30t is equal to 200 plus 40t minus 400. We then just collect the t's on one side and all the numbers on the other side. We end up with 10t is going to be equal to 200, therefore t is 20 seconds. So it's going to take 20 seconds for the police car to catch up to the speeding car. Part B, the distance covered when the police car catches up to the speeding car. I mean, now that you have the value of t, it's pretty easy, this second part. Okay, so we've got the displacement of the car is 30 times t, which is 600 meters. That's the answer. Okay, the answer is 600 meters. But let's put that 20 seconds still back into the expression for the police car. Okay, just to confirm, because it should also be 600 meters, because the values of displacement should be the same. Okay, so we'll put our 20 seconds back into our displacement for the police car. Okay, so we end up with our half times 4 times 10 squared, because it accelerates for 10 seconds. And there's going to be plus 40 outside of 20 minus 10. Okay, so if it accelerates for 10 seconds and the total duration of its journey is 20 seconds, then it's going constant velocity for the remaining 10 seconds. Lo and behold, it becomes 600 meters. So the displacement of the car and the displacement of the police car are the same. Awesome. We can, rest and we can fall asleep at night knowing that we've solved the problem correctly. Okay, so part C is the tricky one. The final speed of the police car when it catches up to the speeding car if the police car continued accelerating at 4 ms to the minus 2 indefinitely during its chase. All right, you math purists, you're going to get upset at me. Please don't tell the Sydney Centre of Math that I have just done what I'm about to do, because there might be some unsavory acts towards me in the future, okay, if this gets out. Okay, so we're going to say here that 30t is equal to a half at squared. Okay, those values of t are going to be the same. The police car doesn't go any constant velocity stuff, it just keeps accelerating. All right, so 30t is going to be 2t squared. Awesome, 2t squared minus 30t is going to be equal to 0. All right, because they have to be equal to each other. Just ignore this bit. Yep, cool. T1 is equal to, T1 outside of 2t1 minus 30 is going to be equal to 0. Then may or may not have divided by a certain number there. T1 is therefore going to be equal to 0, or 2t1 minus 30 is going to be equal to 0, and therefore t1 is going to be equal to 15. Okay, so they're going to have equal displacements at t is equal to 0, which makes sense because that's when the car goes past the policeman, and equal displacement also after 15 seconds, because essentially that's when the police car will catch up to the naughty people in that really fast supercar. All right, so then we say v is equal to u plus at. Okay, it's accelerating at 4 for 15 seconds. Therefore, the final speed is going to be 60 meters per second. Okay, it says speed, not velocity. You don't need to give it a direction. All right, cool. There we go. That is our first 5 in 20. Hopefully you guys found that interesting, to say the least. Hopefully you found it helpful. Hopefully we got pretty close to being 20 minutes. Okay, if not, I promise I'll do better next time. All right, so that's it. That's our first bit of SUVATs summed up.